So when we think about calculus, sometimes calculus is described as the mathematics of change. We try to understand and measure and predict how things are changing. And of course, that's a very applicable task because the world around us is always changing. Anything of interest that we're looking at in the world is changing. And so we don't often get to look at something in a static or unchanging form because the next instant of time it will have changed and become a different take on a different value. So sometimes studying change is difficult because sometimes that change is very, very slow, like the formation of a mountain or the melting of glaciers. Sometimes it's fast. The changes that happen at the subatomic level. Sometimes it's in between, like how is you take some Tylenol for a headache, how is your pain level changing over time? But in all of these instances, we would like to figure out and predict and measure how fast things are changing so that we can make predictions. In the case of the headache, you would like that headache to go away very quickly, and so you'd be interested in developing drugs that cause that to happen without any kind of bad side effects. So when we talk about studying change in calculus, we are kind of talking about two different kinds, at least in Calculus 1. We talk about two different kinds of change. We talk about average rate of change, and then here in a moment we'll talk about instantaneous rate of change. So the average is, how is something changing over a period of time? And then the instantaneous is, how is something changing right now, this very instant? And so we have some mathematics that we can do to find these rates of change. So what we want to study, at least to begin with, is how functions are changing. Okay, how the graphs of functions are changing. And so you see here a graph, and this of course is the graph of y equals 1 over x. And notice, as x's change, y's are changing, and we can recognize the change in the y values by the drop or the rise of the function. So the fact that that function is not just horizontal tells us there's some change going on. A horizontal graph, there's no change going on, right? It's always the same height, or the y value is always the same. But look, this graph is dropping there, and it's actually dropping there again as we move from left to right. So the graph is changing. Now we can kind of talk about how it's changing. Notice in this area it's dropping quickly. So it's changing very fast, right? We've only covered this much distance on the x-axis, and look how much distance we've covered on the y-axis. So rate of change is always a comparison between how you are changing on the y-axis versus how you're changing on the x-axis. So in that little section of the graph where it's very steep, there's a high rate of change, right? We kind of get a moderate rate of change in there, and then finally over here it's not changing very much, right? It's, as we've only dropped this much as we've traveled this much on the x-axis. So rate of change is actually how is y changing versus how is x changing. Okay, and the nice thing about having a graph and talking about the rate of change of graph is you can kind of put it in common language. You can kind of think of it as how steep the graph is. Very, very steep there, so that's a high rate of change. Then it's getting less steep, a moderate rate of change, and then it kind of just getting flat, and that's less rate of change. So when we talk about rate of change, we could kind of substitute the idea of steepness of a graph, right? Or steepness of a hill or a climbing path. Those would represent situations where there's a high rate of change. Okay, so if we want to talk about the average rate of change, we need, first of all, two things. We need a starting point. Let's pick this point right here as our starting point. okay, and then we need an ending point, and I don't know, let's pick this point. Now if we look carefully at this graph, we'll see that this point right here, this first point, is 0.25. That's the x coordinate, right? Because, oh, excuse me, let's back up. That's 0.5, right? Because this is 1, and so each of these tick marks represents 0.5. So let's see, if x is 0.5, plug that into our function, and that tells us our y value is 2. Of course, we can see that right there. So our starting point, we need a starting point, and it's a 0.52. Our ending point is at, well, looking at the graph, we see that that's 3, and then if x is 3, plugging it into the function, that tells us the y coordinate must be 1/3. Alright, so to find the average rate of change, you need a starting point and an ending point. Now, this is an algebra concept, so you'll remember this from algebra. Basically, what I'm going to do is I'm going to figure out, hey, how much did I change vertically? So the average rate of change is, I'm going to say, what was my change vertically in between these 2 points? And to find that vertical change, you're going to ask yourself, what's the difference between the ending y value and the beginning y value? So my ending y value, ending y coordinate, is 1/3. Subtract the beginning y coordinate, so that's 1/3 minus 2. And so if I actually calculate that, right, do a little conversion to fractions, we've got 1/3 minus 6/3, that's what 2 is, or minus 5/3. So that means we dropped from starting to ending 5/3 units, 1 and 2/3 units. Alright, so that's my vertical change. So to find the average rate of change, I not only need how much did I drop vertically, but I also need to find out how much I changed horizontally, and I'm going to create the ratio of those. So vertical change on top of the fraction, horizontal change on the bottom of the fraction. So now I'm going to be finding the difference between the ending x coordinate and the beginning x coordinate. So 3 minus 1/2 looks like that, and of course that's well, let's write this 3 as a 6/2, and that is a 5/2. And then so that means, again, if I look just purely at those numbers, that means from my starting to my ending point I dropped 5/3 over a horizontal span of 5/2. Now I can clean that up, right? Minus 5/3 over 5/2 turns into fractional division, so invert and multiply. So minus 5/3 times 5/2, do that division is what we're doing, is going to become a negative 2/3. And that is my average rate of change over that period, and sometimes we'll just describe it in terms of x's. Sometimes we'll say over the interval running from where x is 1/2 to where x is 3. Minus 2/3. That means we drop 2/3 of a unit for every 1 unit we run horizontally. Now, this language should all come together if you think of what we've just done. What we've done is something very common in algebra. We basically calculated the rise, that's the vertical change, over the run, right? And in fact, the formula for the average rate, the formula for the rise over the run, or the slope, right? This is the slope from algebra, is y2 minus y1 over x2 minus x1. And that's just exactly what we did. So if I want to find the average rate of change between 2 points, basically what I'm doing is I'm imagining a line through those 2 points, and I'm finding the slope of that line using the rise over run method. And so that's the slope of the line represents what the average rate of change was, right? And if you look back at this interval here, we dropped some, right? That's a negative slope, and it was pretty steep there in the beginning. Here in the end, it was fairly shallow. So on the average, we kind of hit the middle, which was a minus 2/3. So that's how we find the average rate of change of a function over a time interval. Okay, so now we're going to change to finding the instantaneous rate of change. So the difference here, we're going to use the same graph, y equals 1 over x, the same function. The instantaneous rate of change is, first of all, we're not looking at the change, the average over between 2 points. What we take when we're looking at the instantaneous rate of change is we look at 1 point and we say, hey, how steep is the graph at that point? How steep is that graph? I mean, think about it. If you're walking along this graph right here, it's going to be pretty steep up here, and then down here it's going to level out. But at all times you kind of have this idea of steepness, and so we want to come up with a number for that. And so the instantaneous rate of change is that number. How steep is the graph at a given point? So to find that, we have to come up with one other idea that can kind of help us. And the idea is this. We talk about what's called a tangent line. If I take my curve here and I take a straight line, there is one line and one line only that just comes along and touches the curve at that point. Okay, it's just touching only at that point. So that's called the tangent line. Right? So at any point on a curve you can find the tangent line. Say I go right there. What's the tangent line? Well, I'm at least drawing it in here. It's right there. It may not quite look like it, but it should only be touching that point at one line, or that graph at one point. So very simply, here's the task. If I want to find how steep the curve is at this point, what I need to do is find the slope of the tangent line. And the slope of the tangent line is the slope of the curve. Okay? The reason we talk about finding the slope of a tangent line is we know how to find slopes of lines. We just talked about it using that rise over run method, the y2 minus y1 over x2 minus x1. Okay? So to find this rate of change, here's what I'm going to do. I have to have 2 points. That's the challenge. I have to have 2 points in order to use the slope formula. I need a y2 and an x2 to go along with my x1 and y1. So the idea is this. I'm going to find an instantaneous rate of change, I'm going to pick some point on the curve, away from the place I'm trying to find the steepness of, right? Now, take those 2 points and draw a line. Imagine a line going through those 2 points. Let's see if we can do that a little better. Okay, well there's a line. It should have a slope. Okay, so let's find the slope. We know how to find the slope. It's just going to be the difference between the x and the y coordinates. So let's see. Our initial x, our x1 and y1 are always going to be the point we're looking at. All right, so in other words, we want to find how steep, we want to find the instantaneous rate of change or the steepness of the curve at the red point 1 1. So that's always going to be our x1 y1. So now we just picked a second point on the curve. That's the key. It's got to be on the curve and a little bit away from our first point. So the point I chose there is somewhere in the neighborhood of 0.25 as the x coordinate, right? And so if x is 0.25, then that means, plug it into our formula, that means the y coordinate must be 4. So again, this point is about 0.25, 4. There's our second point. So what's the slope of that line? Let's call this L sub 1. Well, we know how to find the slope of that line. Change in y over change in x. So I'm going to go change in y. So we'll just write this as the slope column. Change in y is 4 minus 1 over change in x, 0.25 minus 1. So that's a 3 over 0.75. And if we do a few calculations, that's going to be what, 4? That's the slope of that line, right, of L1. Okay, so there's the slope. Now, here's what you need to think about. This slope is not equal to that slope, clearly, right? The steepnesses are not the same, but it could be used as an estimate. Maybe not a very good estimate, but you know that slope is 4, and maybe this slope is not quite 4. Oh, we're missing a negative sign, so you're going to have to forgive me there. That's a negative 4. So what we've got in the negative 4 is an approximation to the slope of the tangent line. Not a great approximation, but a slope. But we want to keep track of that number right there. Okay, so the game is this. All right, if I want a better approximation, then what I'm going to do is I'm going to pick a point that's a little closer than the first point. And now let's draw a line through this new point and x1, and now that's a new line, and you'll see that that new line, L sub 2, has a slope that is similar or even closer to the original slope. So we play the same game. If I want to find the slope of L sub 2, I'm going to come along and I'm going to say, okay, the first point is still 1, 1. Second point, if you look at it, it goes through the x-coordinate of 0.5, and that means the y-coordinate is 2. So its slope is going to be y2 minus y1 over x2 minus x1, or 1 over negative 0.5 or negative 2. So that's the slope of L2. And you can see graphically that it's closer to the slope that we want. Right? Let's just call the line that we're after L sub 0. That's the one we want. That's the slope we want. It's a better approximation. Well, can I get a better approximation? Yes. And the way I do that is by picking a point that's even closer. Now we're getting in that neighborhood. Now let's see if we can identify that point. I'm not going to put any more lines on the graph. So let's see, our first point is still 1, 1. Our second point is now, let's see, we've gotten a little closer. We were originally at x equals, take a look right here, x equals 0.25 and then x equals 0.5. I'm trying to get closer to x equal 1, right? So let's say I choose, and it's not totally accurately depicted on the graph, but let's say I choose this value. That's certainly closer to 1 than 0.5. Not 0.1, 0.9. And so if I choose x as 0.9, then and that's this point right here, 0.9, then that means its y coordinate is 10/9, right? Because 0.9 is 9/10, so 1 over 9/10 is 10/9. So there's my point. So let's find the slope of that new line. I'm not going to draw it in there, that goes through the orange point and our original point. So y2 minus y1 over x2 minus x1. So let's see, 10/9 minus 1 is 1/9. And then this on the bottom is a negative. So it's a negative, so it's a point, so it's a 9/10 minus 10/10, so it's a negative 1/10. So it looks like this is going to be a negative 10/9. So we're getting kind of small there. I can slide this over. So this slope is negative 10/9. So keep track of that, right? It's a better approximation because that line is closer to the original line. Okay, let's do it again. Original point is 1, 1. Let's pick a second x value that is closer to 1 than 0.9. Well, how about 0.99? All right, so that makes this 199ths. If you plug in 0.99 into the function y equals 1 over x. And so what's the slope going to be? We're starting to use up some room here. 199ths minus 1 over 0.99 minus 1. Alright, so we've got on top 1/99th over the bottom, which is a negative 1 over 100. And so in the end this is a negative 100 over 99. Or what is that? That's about a negative 1 and 1/99th. Okay, now I'm going to let you fill in the blanks, but let me show you what the next one, if I pick a point that is 0.999, that's even closer to 1, right? I'm just getting close to 1, and that's going to lead to this kind of y value, and it's going to lead to this kind of slope. Okay, and so now remember what we did. These slopes are approximations to the slope of the tangent line. And supposedly, or I don't think we need to say supposedly, we can see due to the graph, they are better and better approximations to the slope of that line. So what we need to do is just figure out where those numbers are going. Is there a pattern there? Are they headed to a specific value? And I think if you look closely, you'll be able to see that, hey, -4, -2, that's not much there. But now this first one, if we write them down in decimals, look what they become. This is negative 1.1. This is negative 1.01. This is negative 1.001. It looks like these numbers, I think the next one, right, we could predict would be negative 0.0001. What are these numbers doing? They are getting closer to 1. They are going to, negative 1. And in fact, that is the slope of our line. That is the slope of the tangent line. It's the slope of the curve at that point. It's the instantaneous rate of change of the curve at that point. Now there's a little bit more to this, but by and large this is what we're doing. If I want to find the instantaneous rate of change, I come through and I start with the point I want to find the instantaneous rate at, and I pick a point that's close to it, and then I pick a point that's closer than the first one, and then closer still, and then closer still, and find the slopes. Or I find, really what I'm doing is I'm finding the average rates of change over a shorter and shorter time period. Think about that. From 0.25 to 1 is this one. That's the time period, or the interval on the x-axis, 0.25 to 1. Here it's from 0.5 to 1. Here it's from 0.9 to 1, right? That's a smaller gap on the x-axis. We're closing the gap on the x-axis. There's a smaller gap, 0.99 to 1, and we're asking what is happening as we close the gap on the x-axis, what is happening on the y-axis. And then we look at that ratio and we see where these numbers are going. They're headed to negative 1. The smaller we make that gap, the closer we're going to get to negative 1. And so that process done infinitely will show us that slope must be negative